So we've talked about how linear independence and orthogonality are good properties for a set of vectors to have. So this exercise will sort of explore the relationship between orthogonality and independence. Okay? So suppose S is a set of vectors, and it's a non-zero set of orthogonal vectors. What we want to do is show that S is linearly independent. Okay, so given a set of non-zero orthogonal vectors, show that they're always automatically also linearly independent. Okay. So since we don't know much about these vectors other than they're orthogonal, we're going to need to use the definition of independence to prove they're independent. Okay. So for the vectors v1 through vq, I'm going to write down the dependence equation. So it's the starred equation from previous lectures. Okay, and I'm going to ask, what could the CIs possibly be? Since we're trying to prove it's independent, we want to prove that the CIs can only be 0. Okay, remember, that's the definition, that the only solution to this equation is that the C's are all 0. Okay, so this is how we're going to prove it. Okay, so we're going to let I be just represent one of the numbers between 1 and q. Remember, there's q many vectors. Okay, so this is what we're going to do. We're going to take the dot product of this equation with a vector vi. Remember, the I comes from one of these numbers. Okay, so we have a vector equation here. Okay, so I'm allowed to take the dot product of both sides. Okay, and it'll maintain the equality, right? Okay, so I'm going to take vi dot this, the left-hand side, equals vi dot the right-hand side, the 0 vector. Okay, so scroll down. So on the right-hand side, we have a vector times a 0 vector. That's always just the number 0. Okay. Left-hand side, we have vi dot the linear combination here. Okay, and then I'm going to need to use the distributive rule, which says I can distribute the dot product over the sum as you expect. Okay, and this is the sum you get. Okay, so remember, I was chosen to be one of these numbers from 1 to q. Okay, so I is one of these summands here. So one of these, I'll just write it to be in the middle somewhere. For one of these, I'm going to be taking vi dot itself, vi. Okay, and the rest of them are going to be vi dot a different v. Okay. Okay, so this is the sum. If you're concerned about the order I've written the constant and the dot product in, if you remember, there's a product, there's a property of the dot product we mentioned that says, you know, if you have a scalar attached to one of the vectors of a dot product, you're free to move that scalar around and it doesn't affect the result. Okay? And you're also free to swap the order of the vectors that you're dotting. Okay, so you can rewrite this as this, and it's okay. Okay, so now we're going to use the fact that S is an orthogonal set. Okay, so remember, what does orthogonality mean? It means that if I take any pair of distinct vectors in the set, the dot product is going to be 0. Okay, so since the v's are orthogonal, if I have vi dot vj, and I doesn't equal j, the result of that dot product is going to be 0. That's just what orthogonality means. Okay, so for every dot product here where it's vi dot something that's not I, we know those all are going to be 0. It's going to be 0. This is going to be 0. So all these terms disappear. Okay, the only one that won't disappear is vi dot itself. Okay, that won't be 0. Okay, so this is all that's left. Okay, so, well, what is vi dot vi? We don't know, but we know it's not 0. Okay, why? Okay, since vi is not the 0 vector, remember we're assuming the set has no 0 vector in it, that means vi dot itself is non-zero. Okay, so remember, only the 0 vector has length 0, and only the 0 vector will be 0 if you dot it with itself. I think that's straightforward from the dot product formula. Okay, so that forces ci to be the number 0, right? Because this is an equation of real numbers. I have ci times a non-zero number equal to 0. That forces ci to be 0 in this case, right? If it was ci times 10 equals 0, well, then you know ci has to be 0, right? Okay, so that proves that ci, our constant, is 0. Okay, and that argument works no matter which index 1 through q you choose I to be. Right? You can repeat this argument for any of these numbers and it'll always work, right? So since all the c's are 0, okay, that's what we wanted to show. This is the only solution to the dependence equation up here, okay? And that exactly means that this set is a linearly independent set. And that's what we wanted to prove. So during the lecture, we talked about normalizing vectors. And we mentioned that the normalized vector of v, which is this expression here, 1 over the length of v times the vector v, was always a unit vector. That is, it has length 1. Okay, so in this exercise, we'll verify that that's true. Okay, so suppose v is non-zero. We want to show that this vector here has length 1. Okay, so start out with v. V has coordinates that looks like this, right? So what does the normalized vector look like? Well, 1 over the length of v, that's just a number, okay? So we just multiply that number times each one of its coordinates like this. So this is what the vector in question looks like. Then we remember the formula for the length of a vector. Okay, so we have a vector x. The length is equal to the square root of the dot product times itself, which is equal to taking the square of each of its coordinates, summing them up, and then taking the root of all that. Okay, so we're going to do that to our normalized vector here. Okay, so we take the square of each of its coordinates like this, and then sum it up. And then we notice that we're taking the square of a fraction, so that's the same as the square of the numerator divided by the square of the denominator for all the parts here. And then for each term here, I noticed that they all have a common factor, 1 over the length squared. Okay, so I'm going to factor that out of all of them, and I'm left with this expression here. Now, I'm going to use a property of the square root, or property of exponents. So, square root of a product is equal to the product of the square roots. So I can write this like this, right? So this part over here should now look familiar, right? What is this? This is the form of the length of v, right? That's what this is. Okay, so now all I have to do is look at this part here. So taking the square root of 1 over the length of v squared. So I can just take the square root of 1 and the square root of the length of v squared, which simplifies to just the length of v. Okay, so what I get is the length of v divided by the length of v, which is 1, right? So this shows that when we do this normalization process on a non-zero vector, the length actually is 1. So this is a picture of normalizing vectors. So this is in R2 in the plane, and this circle here is the unit circle. Okay, so every vector of length 1 in R2 is on this circle. Okay, so let's think of the vector v. Okay, suppose this is v. Then when I normalize it, it becomes this vector here, which is now of length 1, so it's on the unit circle. And here we had to shrink v to get it on the unit circle. Here's a vector u, and when I normalize it, I stretch it so that it's on the unit circle here. Okay, and we can do that with any non-zero vector on the plane. We can get it so that it's on the unit circle of length 1. Okay, so what's the advantage of normalizing vectors? So many important properties of a set of vectors is unaffected by scaling them by a non-zero constant. So orthogonality doesn't change if you scale a set of vectors, and by that I mean multiply any of them or all of them by a non-zero scaling factor. Orthogonality doesn't change, linear independence doesn't change, and the span of the vectors doesn't change either. Okay, so the span of the vectors is actually a subspace, and we'll get into subspaces later. So a lot of the important properties of a set of vectors is unchanged by scaling. Okay, since vectors of unit length 1 are nicer to work with, have nice computational properties, there's usually no harm in scaling it to be unit length.